My name is Konrad Kamiński. I work for Allegro, so we're the largest Polish e-commerce company. And today we're going to talk about asynchronous programming with Kotlin coroutines. So before we start, I just want to ask one question. So how many of you actually used Kotlin, the language? OK, great. So we're going to see quite a lot of code here. So for those of you who don't know Kotlin yet, I'll try to explain some more difficult stuff. So let's start with some code. So here you see a very simple code. So we have a function which tries to send an audit message. So for a particular user, it does three things in sequence. So first, it tries to get the account ID of that user by using the getUserAccountID method. Then it tries to get the product count, which is assigned to this account. And then it sends this audit message to some external system. And this function looks quite simple. It's simple because it just does three things in sequence. But there is a problem with this function if you imagine that all those three functions, if they access some external service. So they have to go over a network to get some data or to send some data. Because this code is synchronous. It's a blocking code. So essentially, if you have a thread which executes this code, then in those three methods, the thread has to be blocked to wait for the response from the server. So it sends a request, for example, give me the account ID, and then it's just blocked, waiting, for example, on the socket to receive the response from the server. And so if you have one of such threads, that's not really an issue. But today we live in a world where we have applications and systems which can actually serve concurrently many users, like millions of users. So we could end up in a situation where we would need like millions of threads which do nothing but are just blocked waiting for the response from some other servers. And it's actually not doable on contemporary machines because each thread, it consumes some resources. So for example, each thread needs its own stack. So we're talking about roughly 1 or 2 megabytes per thread. So with, let's say, millions of threads, you'll get like a very large number, essentially, of memory. Contemporary machines don't have this much memory. And furthermore, there's a pressure on the OS kernel scheduler to schedule those threads. So if you add to it things like context switches between threads, which make, for example, using the CPU cache, it makes it use it in a very inefficient way, then you can see that you can't really write these kinds of applications in that way. So how can we write them? So the answer is asynchronous programming. And asynchronous programming, it comes in many forms. So for example, the first one, which is very straightforward, is to use callbacks. So with callbacks, your functions, instead of returning a value, they return nothing, but you provide an additional parameter to your functions, which is a callback. And once the result of this function is available, we just call that callback with this result. So it's quite a straightforward solution. Here you can see the same code that we've seen on the previous slide, but with callbacks. Callbacks here are actually created using Kotlin functions. So, but with callbacks, you have a different set of problems. So the first one you can see actually here, this is something called callback hell. So essentially what you have is, if you use callbacks, you have these nested lambda expressions here. So at the end, you have these curly braces, and the whole code looks like a tilted Christmas tree. And here we don't even use things like conditional statements, like exception handling, like loops, which would make this code even more even less readable, and more difficult to read, and even more difficult to write. So what else can we do? So we can use something which is called a promise object. And it also comes in many forms. So for example, here you can see the same code, but with completable future. So a promise object is something which will eventually return a value, and you can somehow react to this fact that the value is returned. So here, for example, we have a completable future. Our functions now, instead of returning a value, they return the promise object, which is the completable future. It's the standard type which is available in JDK. And now our code looks a little bit better because we don't have these nested callbacks. The callbacks are actually on the promise objects. So we have the thenCompose method, which is called, and you pass a callback to this thenCompose method. And the code inside this thenCompose is called whenever the value of getUserAccountID is returned. And the same applies to thenAccept, which takes as a parameter a function as well. So now our code is a bit better than the one with callbacks, but still, you see, the problem here is that first of all, you have to learn all those. We call them combinators. So they are like different methods which react on different events. Like, for example, if we had an exception thrown from the getUserAccountID, then you would have to use a different method which reacts to an exception. So you have to learn all of those different kinds of methods on your promise object. And if you use completable future and you learn it, and you try to use a different kind of promise object, like, for example, the reactive libraries like RxJava or Project Reactor, they all work on the same principle. So the things like the types like single, they are all sort of like promise objects. And then you have to learn a different set of methods because single type has different set of methods than completable future. So that's one problem. You have to learn all those different combinators and how they work. The other problem is that now your code mixes business logic with infrastructure logic. So here you have business logic in the form of those three methods, and you have infrastructure logic in the form of those thenCompose, thenAccept, etc. So it's less fluent to read it, it's very difficult to write it, and if you want to add things like, for example, retrying calls to some method if it throws an exception, it becomes really a pain. So what can we do to alleviate this problem? So in Kotlin, there is a new concept. Well, actually, the concept is old, but the implementation in Kotlin is new, and it's coroutines. And to create coroutines, you use suspending functions. So coroutines actually is an old concept. It's almost like 50 years old. It's been introduced in the Simula language. And in Kotlin, it comes in the form of suspending functions. So now our functions, if they are suspending, they can suspend its execution in certain points. So here you can see the same kind of code that we've seen at the first slide, but now our code is asynchronous. And it's done only with one keyword, which is suspend. So our sendAuditMessage function can now suspend when it calls getUserAccountID or getProductCount or sendMessage, because all those three functions are suspending. And by suspending, I don't mean that the threads that will execute it will be blocked. There is no such a thing as blocking a thread, because coroutines can suspend execution in one thread and resume execution in a different thread. So in order to understand how this suspending works, we have to go deeper. We have to look at how the Kotlin compiler generates the code of this function. So first, we have to look at the signature of the function. So if you have a suspending function like sendAuditMessage, in the bytecode generated by the Kotlin compiler, the function looks a bit different. First of all, it has an additional parameter, which is of type continuation. I call it callback because essentially it's a callback. Previously, we've seen the code with callbacks in the form of a function. Here, it's an interface, but essentially, it's the same thing. So if send audit message now wants to return a value with the usage of this callback, it should call one of the two methods. It can call resume, so it will mean that the send audit message returns some value, or it can call resume with exception, which means that send audit message wants to throw an exception. There is also this context, coroutine context, which tells how this coroutine should be executed, what threads should be used, what's the context of execution of this coroutine. And there is one more thing which is different from the original signature, and this is this any parameter with a question mark. Now, question mark in Kotlin means that the value returned by this function can be null. And any is essentially the same thing as object. So our function now can return any object, and it also can return null values. So why is it like that? Now, sometimes our suspending functions may want to not suspend at all. They just want to return the value. And in that case, they are able to do it because if we can return any value of any type, then we can just return the value directly. We don't use the callback then. But if we suspend the execution and we want to return the value via this callback, we have to somehow inform the caller of our function that the true value will be returned with the usage of this callback. So this is why we have this special value called coroutine suspended. And this special value is returned by the suspending function when it wants to inform the caller that the true value will be returned via the continuation parameter. So let's try to look at the code as it is generated by the Kotlin compiler, the code of our simple function that we've seen at the beginning with suspending functions. Actually, this code is not essentially the same as it is generated by the Kotlin compiler. There are some things which are missing here because they wouldn't fit on one slide, and they would make this code more complex. So here, we assume that the return values of our functions are always returned with the usage of this callback, so we don't have the situation where the value is returned directly. We don't handle that situation. So our function, our suspending function, when it is compiled into a state machine. It is compiled into a state machine because essentially, if we want to suspend the execution, we have to store the state of this execution somewhere. And the state of the execution consists of several things. So we have things like the parameters of the original function. So we have this user ID here. We have the original callback, which we have to preserve so that when we finish executing our suspending function, we should call the resume method on the callback that was passed to our function, our send audit message function. We have label. Label is something which says roughly in what line of the code we are currently executing, so that when we suspend the execution and we want to resume it, we will know from what point in our function we should resume the execution. We're going to see it in a while how it works. And we also have to store in a state the values of our local variables of our function. So here it's account ID and product count. So let's go and see how it works line by line. So first, our state is 0, which means we are at the beginning of the execution of our suspending function. Label is 0, so we go to the case where we check the value of the label. And the first thing we do is we set the value of the label to 1, because the next time the execution will resume, it will be after the get user account ID is called. So then we should proceed from that point after get user account ID. So we set the value of label, which is our state, to 1, and then we call the get user account ID function. Now, this function is a suspending function, so it needs a callback. And this is one thing which I haven't talked about yet, is that the state machine actually implements continuation interface. So we can pass, as this callback, we can pass the state machine, so that when the getUserAccountID function, when it resumes, when it wants to return a value, it will call the resume method on our state machine. And in our state machine, we can see now that the label is 1, so we can continue executing the code. So let's go to the next step. So we set the label to 1. The getUserAccountID function, it called the resume. It called the resume to return the value. The value is stored in the value parameter. So we check the value of label. Now it's 1 because we set it to 1. It's 1. So we set it to 2 because the next time the suspending function will resume, it will be in the next line. We store the value that was passed to us from the getUserAccountID function. We store it in the field of our state machine, in the account ID field. And then we proceed further. So we call the second function, getProductCount. And here the function also expects a callback. So we pass the state machine. So we don't have to create a new callback every time. Like back when there was this code with callbacks, every callback was actually a new instance of an object which represented this function. So for this simple code, we needed like 3 different objects. So there's like pressure on the memory allocation or garbage collector to put in this kind of solution. Now here, we only have one object, which is this state machine, and it's reused every time we call a suspending function within our send audit message. So we call getProductCount. We call getProductCount, we pass the state machine, and when the getProductCount finishes its execution, it calls resume. So the label is now is 2. So we go to this case where the label is 2. We set the label to 3, which is our final step. So the 3 is actually the point where we should finish our execution of the send audit message. We store the product count from the value that was passed as a result of getProductCount, and we invoke the third method, the send message method. We pass the state machine as a callback, and when the send message finishes its execution, the label is 3, so now we know we are at the end of the suspending function. So we've executed the whole function, and now we can call resume on the original callback that was passed as a parameter to send audit message. So here it is. Here's how Kotlin compiler compiles such suspending functions. So this code, the generated code, is quite complex for our very simple function, but the nice thing is that you don't have to explicitly use callbacks here. So you write your code in a regular way, like if it was like blocking a synchronous code. And you can use any constructs of Kotlin language in your suspending functions. So you can use conditional statements, you can use loops, you can use exception handling. Anything that's allowed in a regular language, you can use here. And this is the strength of using coroutines to write asynchronous code. You don't have to learn anything new, like some promise type objects API or something. You just write your code the same way as you used to write. So, but sometimes at the end of the day, we would like to have the access to this callback because we need access to this callback to actually write something which, for example, fires off computation on some other thread, and so that when this computation is finished, it will call the resume on this callback. So we need some basic blocks to work with suspending functions. And one of them is called suspend coroutine. So suspend coroutine is this simple function. It's a suspending function, but it takes as a parameter a function or a lambda. And this function, as a parameter, has this callback. So, for example, if you want to write a function which accesses this callback and calls the resume, it can be easily done. And you can actually call the resume method in that lambda expression. You can use it directly, within the same thread, but you can also pass this to some other computation or some other thread, and that other thread can call the resume. So suspend coroutine will handle both situations. So let's try to write a simple code with this suspend coroutine. It will be simple because it will we're going to write a function, a suspending function, which will just wait for some time. So it will suspend the execution of the function for some time, and then the code can continue executing. So let's write, for example, my sleep as we have a sleep method on a thread. Now we're going to write my sleep, which is a suspending function. So we're going to need delay, and this function should not return anything. Coroutine. Right. So now we have access to callback, and callback is of type continuation of unit, as we expected. And the easiest way to implement this function is to use timer. So a timer is a class from the standard JDK which allows you to schedule tasks. And these tasks will start executing when you want them, after some delay or some time. So we're going to create a timer. And here we're going to use this timer. So after this delay, we're going to call this callback. I'm going to call it resume unit. Right. So now we have our suspending function. It just waits for some time. It doesn't block on a thread because it uses timer, and timer actually uses a single thread for all scheduled tasks. So even if we called mysleep from within many coroutines, we still have only one thread which will handle those delays. So let's try to execute some code with mysleep. So let's call mysleep with, let's say, 5 seconds, and then let's print that. Right. So one more thing, which is very, very useful. You see these marks here, and this mark means that your function can suspend in this line. So for example, here, you see this mark because suspend coroutine is a suspending function. So mysleep can suspend here by calling suspend coroutine. The same thing applies here. So mysleep is a suspending function, so your function can suspend here. But the compiler says that we can't call a suspending function from a regular function. And this is something that we should expect. The suspending function, it has this additional parameter. We have to somehow provide this additional parameter. We have to handle the situation where the return value is returned with the usage of this parameter. So there is this rule that suspending functions can only be called from other suspending functions. So the question is, how do we actually invoke such a function if we want, for example, to invoke it from the main function? So we have to use something which is called coroutine builder. So coroutine builder allows you to create coroutines from suspending functions and execute it. And so the simplest one is called launch. So launch takes as a parameter a suspending lambda, the suspend keyword in the signature of the launch, in the parameter of launch, means that launch takes a suspending lambda, which is like a block of code where you can use suspending functions. And launch itself is a regular function, so we can call it from main or some other function. And launch, it starts executing this code, this suspending lambda, which is passed as a parameter, in the background, some background thread. and it returns a job. So a job is something which allows you to manage the life cycle of a coroutine. So you can, for example, cancel it, or you can wait for it to be finished. There are many things you can do with job. So let's try to use launch to invoke our mySleep function. Okay. Launch. Right. So nothing really happened. I mean, something happened, but the dot was not printed. And again, this is something we should have expected, because launch starts a coroutine. It will wait for 5 seconds before printing something. But the main method, it finishes right away. If we just call launch, launch will create a coroutine, and launch will finish its execution. It has done its job. So main also has done its job. So when the main method finishes its execution, and there are no regular threads in the virtual machine just stops executing. So you have to somehow prevent that the main method from exiting. So we've seen that there is this join function which waits for on the job, which waits for the job to be finished. So we can try to use that. So we're going to assign a job and call job join. But we still have a problem because join is a suspending function. We can't call it from the main method. So we have to use a different coroutine builder, which is called RunBlocking. So RunBlocking, essentially, you shouldn't really use it in your code apart from some demos and unit tests, etc. Because RunBlocking, what it does is it allows you to also invoke suspending functions, but it waits for the suspending lambda that is passed as a parameter to be finished before it finishes. And it also returns the value of this suspending lambda. But for the demo purposes, we can actually try to use it. So let's go back to our code and try to use RunBlocking. Okay, now it should compile. And let's see what happens. 5 seconds, and there is a dot. So we got a success. Great. So we have our first coroutine running, and we know how to write the code. Now, some people call coroutines lightweight threads, and it is for a reason, because coroutines and threads, they are very similar. So in a thread, you just run a piece of code, and the thread blocks for some time, for example, if it waits for something. And the coroutine also, it's like a piece of code executing, which can be suspended at some point. So there is a similarity here. Also, you can have many threads running concurrently, and you can have many coroutines running concurrently. So what's this lightweight? What does it mean, this a lightweight thread? So let's try an example where we're going to create many threads or many coroutines and try to compare how they work. So first, let's try to create like 100,000 of coroutines with just print a dot and see how it behaves. In Kotlin, it's quite simple to do. We'll just create a list of 100,000 of jobs, and it's jobs. And each job, for each job, we will then join, which will mean that we will wait until all those 100,000 of coroutines finish its execution. So what should happen is that after 5 seconds, we should have like 100,000 dots printed here. So let's try if it works or if our VM crashes or something. I don't know. Okay, let's see what happens. Yeah, there are some dots printed. So I don't know if I'm going to count them. But, okay, you can try that. You're going to exit the presentation mode. You're going to go to the end of the line. And here, I don't know if you can see it. You can't? There's a piece of it only displayed. Right, so you have to believe me. There's 100,000 dots here printed here. So it worked. Great stuff. Now let's try to do the same thing with threads. So it only requires a few changes in our code. So obviously we won't be needing the RunBlocking because there will be no coroutines here. We're going to have not jobs but threads. And instead of launch, we're going to use thread. So thread is a function in Kotlin which creates a thread. It takes as a parameter a lambda, and it creates a thread and starts executing this lambda. And instead of my sleep, I'm going to use sleep because this is what we have. This is what we can do to block a thread for 5 seconds. And that's about it. Let's try and see what happens. Okay, so there's something in the red. Okay, so we have some dots. So now we have, how many dots we have? 2022. And how does it work? Okay. And we have an exception, out of memory error, unable to create a new native thread. So you can see that we reached the limit of the number of threads which can be allocated on my machine. Actually, I could increase it a bit. I mean, I could increase the memory that is assigned to the JVM, but it will not go to 100,000 of threads. It's not possible. So you can see that with threads, we can't really do the same thing as with coroutines. And this is why we call them lightweight, because they don't consume that many resources as threads. They don't need stack. They don't need a separate stack. So the only memory they consume is the state in our state machines, in our suspending functions. Okay, so far we've seen how we can write sequential code with coroutines. But with coroutines, you can also write concurrent code. And to do that, we need a different coroutine builder. What we need is Async. Async, just like every other coroutine builder we've talked about, takes a suspending lambda as a parameter, and it returns a deferred object. A deferred object is like a promise. So it's very similar to completable future. There is one function available on deferred, one special function which we'll use, which is await. And await is a suspending function. So essentially what we do is we call async. Async starts executing the coroutine, this code inside the lambda. And then we call await on the result of async to get the result. And since async starts executing the coroutine in the background thread, we can call several async functions and then only call await to gather the results. So again, let's try a simple example. So we're going to get rid of this. We'll use my sleep. But so let's suppose we have a situation where we have two external services. From one, we're going to get some personal details about the user, and from the other, some financial details about the user, and then we're going to get some data and mix them up and print them out. So we'll need financial details. Let's say that there is some amount here, and we'll have personal details with, let's say, a name. Right. And so we're going to need two functions. One will load financial details. And so we'll just simulate the fact that it's suspending. So we're going to use my sleep. We're going to sleep for like 2 seconds, and then just return the financial details. Let's say 12. And we're going to need a second method for personal details. I'm typing too fast. Right. Okay, so here we're going to wait for like 4 seconds and return personal details. Let's say it's John. And so we're going to need to run use RunBlocking. This we're going to call suspending functions. And so we're going to measure the time it takes to actually execute both of these functions. So first we're going to execute them in sequence. For measuring the time that it takes to execute something, there is a very convenient method in Kotlin which is called measure time millis. It takes lambda as a parameter, and it returns the time it took to execute this lambda. So let's call it time millis, and let's call first load financial details. Let's call it financial details and personal details. Okay, and then let's print out, the details that we got. So financial amount. Something's wrong. Oh, okay. What's that? It's name, right? Thanks. Name. Okay, let's split it into 2 lines for readability, and then we're going to just print the time. Okay, so that's about everything we have to do. Right, so let's try it. So now, first we're going to write to execute it in sequence, so it should take roughly 2 + 4, 6 seconds. We have 6 seconds. But now let's convert it to run concurrently. So we're going to use this async coroutine builder. So it's async. Now, async returns a deferred. So our financial details will actually contain deferred of financial details. So we have to call the await to get the result from this deferred. So here we're going to call await, and here the same thing. Right. So let's try to run it now and see how long does it take to execute it. Oh, it's 4 seconds. It's 4 seconds because which one was it? Load personal details takes 4 seconds. So we have to wait at least that time to finish the execution of the coroutine. So this is the way to write concurrent code with coroutines, and it's been done this way because the designers of coroutines in Kotlin, they decided that the writing concurrent code is very difficult. So you should have it put explicitly in your code instead of some black magic. Okay, so we have asynchronous code, we have sequential code, we have concurrent code. But what if we already have an application and we want to introduce coroutines in our application? Because if we start with a greenfield project, it's very easy to start using writing it with coroutines. But if you have an existing code base and we would like to start using coroutines, we need something to interoperate between our solution, our libraries which we use, and coroutines. And fortunately, in the Kotlin X, there's a Kotlin X set of libraries which allow you to interoperate with different kinds of libraries which already exist and that give you this possibility to write asynchronous code. So, for example, here you see 2 examples of that. The first one is compatible fuchsia. So if, for example, you have already an application which expects a completable future somewhere, and you want to create this completable future but use coroutines, then all you need to do is you have to use a coroutine builder which is called future. And future, as every coroutine builder, it just takes a suspending lambda as a parameter. And it returns a completable future. So that in your code, when you want to have completable future but write the code with coroutines, this is the way to do it. And the other way around, if you're using suspending functions, if you're using coroutines, and you want to use some API which provides only completable future, then you can use an await function. So this is an extension function. So in Kotlin, you can have extension functions, which is you can define your own functions on existing types. So here you have the await function on completion stage, and completable future actually it inherits from completion stage. So you can call it also on the completable future. And with await, it actually waits almost in the same way as it does for deferred that we've seen just a few minutes ago. And the same thing you can do with RxJava. So here you can see the code that can interoperate with RxJava 2. You have RxSingle function, which allows you to create single, this reactive type from RxJava. And you can write your code with suspending functions. And you also have the await function, which is the extension function on the single source. So the single sources, single inherits from single source. So you can also call it on single. So, and there's like many more libraries like these which allow you to interoperate with things like Project Reactor or Guava or Retrofit. There's like a lot of them, and you can also write your own. So there are a few things which have not been covered here. So I mentioned coroutine context. So a coroutine context is something which allows you to specify how your coroutine should be run. On what thread, for example. So let's say you want to have a separate thread pool on which you want to run your coroutines. It's quite easy to create a coroutine context from a separate thread pool, and you pass this coroutine context in all those coroutine builders. So in Launch, in Async, they implicitly use fork join pool. This is why we haven't seen it in the code, but you can actually provide your own coroutine context so that your coroutines use special threads. And this is useful in cases like, for example, if you do programming on Android. And on Android, you have to use a special thread to do some things on UI. It's the same thing as with Swing. If you've ever done any programming with Swing, there's a special thread which allows you to do some things which do something on UI. So there is a special coroutine context called, I think it's called UI, just simply UI, that you can specify when you launch a coroutine, and then your coroutine will actually be run on this UI thread, so that you don't have to worry about the fact that some other thread that your code will run from some other thread, and you will do something which is not which you shouldn't. So we have things like mutexes. So if you have multiple coroutines running concurrently and you have some shared state, then you have to somehow manage the fact that only one coroutine can have access to the shared state. If it's not a read-only state, but if it's a shared state which can be changed. So if you use threads, you have a number of options. So you have things like locks. You may synchronize on something. With coroutines, you can't really do that, because if you use locks, your coroutine would be blocked on that lock, and we don't like blocking with coroutines. So this is why you have mutexes. So mutexes, they work very similar to locks, but the methods, the functions which allow you to lock or unlock, they are suspending. So your coroutine will suspend. Let's say that they want to put a lock on an exclusive lock. If that exclusive lock is already taken by some other coroutine, your coroutine will be suspended until that other coroutine unlocks it. So you don't block any thread waiting on that lock. We have channels and actors. So again, if you have multiple coroutines and they want to talk to each other, they can use channels. So it's a concept which is already available in Go. So essentially what a coroutine can do is one coroutine can send a message to a channel, and the other coroutine can receive a message from that channel. We have like different kinds of channels. We have broadcast channels, or like this, or they can just work like a queue. But the nice thing about channels is that the methods, the functions that allow you to send a message to a channel or receive a message from the channel, they are suspending. So again, your coroutine will not be blocked. The thread will not be blocked when it wants to receive something from a channel. It will just suspend its execution. And as I mentioned before, there is a lot of interoperability libraries with different existing solutions. If you want to know more, there's a couple of ways to learn more about coroutines. So the first one is the Kotlin X coroutines GitHub repository. And it contains a set of very nicely written documents about coroutines, like tutorials, guides, and special guides about how to work with reactive programming or with UIs. Really very nicely written. I suggest you that you take a look at this. The other website that you can have a look at is the official Kotlin language reference, where you can find also some information. And there's a guy, Roman Elizarov. So he's the main designer of Kotlin coroutines. So you can Google his talks. There's a number of different talks, like the basic ones or the advanced ones, where you can learn more about coroutines. So this is me, and this is my GitHub account, where you can find, if you use Spring Framework, and one uses Spring Framework. Oh, right. So go to this website. This is the library which allows you to use coroutines in your Spring applications, so that, for example, you can have a REST endpoint as a suspending function, or you can have repositories like those database repositories where your functions are suspending. So it uses underneath many different things. It also allows you to do some things which are not allowed with, for example, Project Reactor, which is now in Spring. So go have a look. It may be useful. And yeah, we have still 2 minutes left. So that's all from me. If there are any questions, yeah, okay.
Yes. So Webflux is getting quite popular now with the Reactor in Spring Boot. So can you use coroutines in that context, or should you choose one or the other?
Could you repeat the first word? So
in Spring Boot now you have Webflux.
Webflux. Okay. So the
choose one or the other, or you can mix.
Right. So the question was, because in Spring Boot, or essentially in Spring Framework, in the 5th version, there is Webflux, which allow you to. Which essentially, it's a way to write web applications with reactive types. And the question is, can we somehow mix those two approaches? And the answer is yes. And so this library actually allows you to, if you just make a dependency on this library, you will be able to use both at the same time. The reactive programming, the reactive types, and the coroutines as well. So yeah, it's perfectly possible. Yep.
I'm not a Kotlin guy, that's a dumb question, but I saw you're using the external package. Does it mean that, so what is
right.
And
Yeah.
it doesn't mean that it's going to change in the future. Like it's not a stable API,
Right.
and it's better not to rely on it. Don't use it broad or something.
Right. Okay. So this is something I should probably mention at the beginning. So the question was about the experimental. In the code, you could see that the packages, the names of the packages are experimental something. So the Kotlin coroutines feature is considered experimental by JetBrains, but experimental. That's probably the biggest mistake that was made to call it experimental because, well, it works. The Kotlin compiler has had it for like a year and a half now, and JetBrains uses coroutines for its internal purposes. So it's like production ready. I think it will be called non-experimental in Kotlin 1.3, but the position right now is that we can use coroutines without, fear that they will change significantly. Because one thing is the compiler, and the other thing is those libraries that we used here. So when JetBrains releases some feature, if they change something, they always provide a migration tool. Now here, it will probably be the same. So right now the position is that in Kotlin 1.3, they will support both this approach. I mean, for example, the libraries with the experimental name in the package, and the normal, regular libraries that will probably be just different, but they will just differ by the names of the packages. So it's really safe to use coroutines right now. So you shouldn't worry. Yep.
So I assume my question is pretty generic in terms of this suspended execution buttons that we use in different languages, but actually the most important in this async coroutine builder. And the question is it possible to cancel execution for the suspended block of code that was already scheduled?
Yes. So the question is it possible to cancel a code, essentially a coroutine, because the question was about async, but it applies to every coroutine.
Yeah, right, but in async, this is essential, so from time to time I need to do that. If I have sequential code that cancel, it is not a problem, actually. But in async context, it might be
let me get back to async. Oh, where was it? Here? So async returns a deferred, and deferred actually it implements job. And on job, you have those methods like cancel. So it doesn't really matter if you use launch or async or something else. If it allows you to call cancel, then the whole canceling actually happens in the same way. So canceling of coroutines, it must be cooperative. So a coroutine has to learn that someone wants to cancel it, and it has to stop its execution. So there was this coroutine scope here, right, where you have this isActive value. So, and this coroutine scope is available in launch and async, essentially in every coroutine builder. You can check if the isActive is false, and it means that the coroutine should stop working. But for example, for things like delays, because we've written our own mySleep function, there's already a function like this, obviously in the Kotlin standard library, which is called delay, and delay actually supports canceling. So if you delay for some time, and in the middle of the delay you'll call cancel on your coroutine, it will just cancel the delay, and the coroutine will finish its execution without executing the rest of the code. Okay, another question? All right, thank you.